positional sensors. So this is a little bit of what we're going to do. We can have potentiometers, volume control, variable resistance, linear, variable, differential, particle, LVDT, encoders, all combined from analog input, variable impedance, equals this is the area you're looking at in terms of an offset to a label distance of rotated potentiometers active so potentiometer. What a potentiometer is a track, carbon track usually. Look at the circuit that's like that. We've got a connection on either end, here and there. And then the third connection is on the wiper that goes on that carbon track. So between the wiper and the end of variable resistance. Simple as this here. Between these two tables, the output signal for the output to those tables is sent. Main advantages: low cost, relatively low tech, easy use. Most current technicians that understand what a potentiometer is and how it works, and so on. Main disadvantage, mechanical wear of moving parts. The accuracy is relatively low, as is the repeatability of reading for the same position. Sensing range is limited by size, unless multi-turn with gearing is used. Cheap carbon track types, subject to electrical norms. The ones we had, the linear straight ones, looked like almost very similar to a rodless cylinder type fare, with like a stainless steel track, so it could slide up and down, effectively lift the track up and down to make the moving part stationary. It would tend on occasion to allow ingress of oil through that seal, and that tends to mess up the carbon tracks as well. And that, they say low cost, but I mean our 400-500 long ones, probably about £300 or £400. So I mean I wouldn't necessarily say that's low cost, but you know, compared to some parts, technically it is. LVDT, right, linear variable differential transformer. What we've got there is a primary coil excited with an AC signal. So that's here, the primary coil, AC signal there. When the armature, the core, moves from one end to the other to a centre position, the output difference between two secondary voltages, so the output is the difference between two secondaries, so we've got two secondary coils. This AC voltage here, with that core going between them, so they're all wound around the same place, it induces voltages in these coils, and the way they're wound is that the output is the voltage of one coil, take away the voltage of the other coil. So that's the difference between the two. So I've got a little simulation on the internet that seems to show that quite well. So as this core moves up and down here, you vary in the amount of induction you get between either the primary coil and coil A or the primary coil and coil B, and therefore in the middle they're both the same, there's no difference between them, and then as you move one end or the other, either coil A gets more induction or coil B gets more induction. And so we end up with there's a null position in the middle, and we can use position either side of the output changing to actually measure how far it's moved from that null position. So in the null position there's no output. In the left position you can see the green, there's a little signal on it, one coil, and it's aligned with the blue. In that position, nothing on the blue. The red one's the primary excitation of the way the output aligns to the green waveform. Yeah? And hopefully this will work. The graphic there showing you the core moving inside the coils, and how the red signal is the excitation of primary, and then you can see how coil A, the blue one, and coil B, the green one, are changing in opposite directions to each other, and the the purpley coloured one is the secondary number one. The blue one take away the secondary to the green. So that's how LVDTs work. Yep. So, moving on. LVDTs. Probes. Frictionless measurement. So unlike the potentiometer, there's no wiper on a track, so there's no friction involved in terms of the movement. The resolution is infinite. Mechanical life, infinite, no friction, not going to break anything. No mechanical hysteresis in terms of change over at either ends. You know what I mean by hysteresis, don't you? You get slack in the movement, like a lead screw, slack in a lead screw. Repeatable, environmentally robust. It can be immersed in liquid, still work quite happily. Insensitive to radial movements. I'll tell you an application where we used to use them in a minute at Fireman. They are sensitive to temperature, not really feasible for longer measurements greater than 500 millimeters. I mean, that's much bigger than any one I've ever seen. The ones we used were measuring a movement of about 10 mil at the most. And they aren't perfectly linear in that measurement. The area mainly I've seen LVDTs used is in a blow molding machine. You want to, sometimes, if there's a shaped container, you want to control the thickness of the plastic in different areas. So where you want more meat around the neck or something, or a shoulder, you want that to be thicker, and then thinner in the body, and then thick again for the base. So what they do is, inside the head, they'd be able to move either the pin, because they extrude it through a head and around a pin to make a tube. They'd move either the head or the pin up and down, just very slightly, and they'd use an LVDT to control that position, with a programmer saying what the profile of the thickness of the pouch was. So the LVDT, very fine measurement of movement, sometimes even only 2 or 3 millimeters on a hydraulic cylinder. But I've seen them 500 millimeters long in catalogues. I've never seen one that long being used. I would have. Well, there's a suggestion that it would be, but the AC is, I think I might say in that previous slide, that ain't like 50 hertz or anything like that, so that's about 10k. Let's just pop back a minute. Have a look. Yeah, primary coil is powered by constant amplitude AC source. That's 1 to 10 kilohertz. Yeah, so it's going to be not that susceptible in terms of what you're trying to do with it to 50 hertz mains. Yeah, alright. Rotary encoders.